Hello everyone, thanks for watching this video, and today's problem is Leetcode problem number 53, maximum subarray. First we're going to take a look at the problem and then few examples to understand the problem better. Then after that we'll go over following 4 ways to solve the problem, that is brute force algorithm, dynamic programming, cadence algorithm, and last but the most interesting one, that is divide and conquer algorithm. I have tried to create a few visualization to show how algorithm runs and basic intuition behind every solution so that it is easier to solve this or similar problem if you come across during the interview. Please do let me know in the comments if you like those and have any suggestions for the improvements. In the end, we'll submit these discussed solutions to Leetcode for the verification purposes. Okay, so this problem has been categorized an easy problem, has a pretty high number of likes. And also this question has been asked in companies like Amazon, Microsoft, Apple, LinkedIn, and Google in past 6 months, which makes it a pretty good problem to look at. And in this problem, we are given an integer array nums, and we have to find a contiguous subarray containing at least one number which has the largest sum, and we have to return that largest sum. And the constraints are given that like the integer array will have at least one element and will have maximum of 3 into 10 to the power 4 elements. And each element in the array will have a negative 10 to the power 5 to the positive 10 to the power 5 value. And also they have asked a follow-up question as well, that if you have figured out the O(n) complexity solution, which we did, then we should try coding the another solution using the divide and conquer approach, and that I'll discuss later in this video, which gives a different perspective to look at the problem. And now let's look at the few examples. In the first example, in the following series of numbers, if we look at the highlighted subarray, which is 4, minus 1, 2, and 1, outputs the sum as equals to 6, which is the maximum sum that you can get from this array. In the second example, we have been given only one element, so that element becomes the output, and that's why the output value is 1. And in the third example, if we sum all the elements of the array, then only we are able to get the maximum sum. That's why the output is 23. Now let's take a look at the algorithm. Here we have two variables, current sum and the max sum, and we have two loops, start locator, which tracks the starting position of the subarray, and the subarray finder tries to find all the subarrays that is possible from the start locator position. For the initial setting, as the first element is -2, the start locator is looking at -2. Subarray is finder is trying to find all the subarrays that is starting from -2. And then we have two variables, current sum is equals to -2 and the max sum is updated to -2. On each step, both variables current sum and the max sum keep getting an update depending on the value of the element. In the second step, for example, the current sum becomes the value equals to -1, which is -2 plus 1. And as the -1 is greater than -2, which is the previous value of max sum, that's why max sum get updated to -1. In the third step, the new element is -3, and the current sum goes down to -4. And as -4 is less than -1, that's why max sum doesn't get an update. As we keep going further until we traverse the whole array and completed all the subarrays starting from -2, after the start locator moves to the value 1 and the algorithm continues until it reaches to the position where the start locator is at the 4 and the subarray finder has explored until the value 1, which happens to be the maximum sum of any subarray in the integer array. After that, the max sum never gets an update, but the algorithm keeps going on until it reaches to the location where the start locator is at 4 and the subarray finder has no more option to explore. As we have only two variables, that is current sum and max sum, which are independent of the size of the array, and the two loops, which makes the time complexity is equals to O(n) square and the space complexity. Now let's take a look at the algorithm. Here we have two variables, current sum and the max sum, and we have two loops, start locator, which tracks the starting position of the subarray, and the subarray finder tries to find all the subarrays that is possible from the start locator position. For the initial setting, as the first element is -2, the start locator is looking at -2. Subarray is finder is trying to find all the subarrays that is starting from -2. And then we have two variables, current sum is equals to -2 and the max sum is updated to -2. On each step, both variables current sum and the max sum keep getting an update depending on the value of the element. In the second step, for example, the current sum becomes the value equals to -1, which is -2 plus 1. And as the -1 is greater than -2, which is the previous value of max sum, that's why max sum get updated to -1. In the third step, the new element is -3, and the current sum goes down to -4. And as -4 is less than -1, that's why max sum doesn't get an update. As we keep going further until we traverse the whole array and completed all the subarrays starting from -2, after the start locator moves to the value 1 and the algorithm continues until it reaches to the position where the start locator is at the 4 and the subarray finder has explored until the value 1, which happens to be the maximum sum of any subarray in the integer array. After that, the max sum never gets an update, but the algorithm keeps going on until it reaches to the location where the start locator is at 4 and the subarray finder has no more option to explore. As we have only two variables, that is current sum and max sum, which are independent of the size of the array, and the two loops, which makes the time complexity is equals to O(n) square, and the space complexity stays at value O1. Now let's take a look at the second solution, which is based on dynamic programming. This gives another perspective by looking backwards, basically opposite of the previous algorithm, which was looking forward. The intuition is that if we look at any element, for example, -1 in this case, if we have the maximum sum possible until previous element, which is 4 in this case, there are two possibilities. Either we have to include the current element, for example, in this case, represented by bottom 4 rows, or we'll be better off with current element itself. For example, when the loop was at the previous element, at that time, the second step was chosen. So basically what we are trying to do here is that we are trying to find all the local maximas at each element, and then final answer is the maximum value of local maxima that we have observed during that whole process. This approach basically reduces one loop from the previous problem. So if we look at this algorithm in action, we have two variables, dp, which holds the local maximas that we have found till now, and maxim, which holds the maximum value of the local maxima that we have found till now. And we have a loop, which is an array iterator, which starts the iteration from the second element. In the first step, we initialize the dp and the maxim with the first number, which is -2 here. And that's why we have dp0 is equals to -2 and the maxim is -2. And then we start the array traversal from the second element. And at each element, we compare these two values, dpi-1 and the current element and the current element. And whichever is the maximum value out of these two, we store that value into the current index of that dp array. And after that, we check whether we need to update the max sum. That will be our final output. So in the first iteration, we have the first element as 1, that we are observing, and the dp minus I minus 1 value is -2. So the sum is become -1, and we check whether the -1 is greater than 1, and 1 gets updated because it's being maximum. And max sum was previously -2, and now it gets updated to 1 because 1 is higher than -2. And then algorithm goes on to element -3, and where the value dpi minus 1 minus current element becomes -2, and the -3, the maximum of them is -2, and because -2 is less than the maximum doesn't get an update. And the algorithm continues until this place where the iterator is pointing at value 1. And here we have the maximum value that we have observed till now is in the previous element is 5. And then we add 5 uh, with the 1. And then we calculate 6. and that is the happens to be the maximum sum that we have observed till now, and that is the output. After that, the maximum never gets an update. And as because there is only one loop, that's why the time complexity becomes O(n), and we have an array which has the same number of elements as the current array that has been passed. That's why the space complexity becomes O(n). Now, if we look at the third solution, which is cadence algorithm, basically the idea remains the same as dynamic program, which we're trying to find the local maximas. But if you observe that at any point of time in the algorithm, we were not looking at the whole DP array. We were just looking at the current element in the array and the previous element in the array. So cadence algorithm basically simplifies it, reducing it into a single variable that is called current sum, and which gets updated by the higher the value of current sum plus the current element or the current element itself. So algorithm starts with a similar initializations. Current sum equals to -2, and the maximum is initialized to -2, and the iterators updates the value if the max of current sum and the current element or the current element is maximum, and the maximum gets updated depending on the value that we have currently. So, and we reach at this position where the maximum gets the last update, and after that there is no updates in the current sum, and iterator reaches to 4. And as you can see, the time complexity stays at O(n), which was a similar as a dynamic programming, but the space complexity has reduced from O(n) to O(1). Okay, the last and the most interesting algorithm is divide and conquer. Till now, we have only looked forward or looked backward in the algorithm, but this algorithm gives another perspective to look at the problem. Basically, the idea behind that is that if we are looking at any element, for example, -1, the subarray with the maximum sum can be on the completely left side of it, or it can be on completely right side of it, which we can find through the recursion of this function. But the third option is that the element is somehow involved with the right and the left elements combined. So for the third point, we have to find a combination of the mid element with the left and right side. First, for the left side, we have to find a maximum sum of the subarray ending at the left element. And this is nothing but the local maximum for that element. On the right side, we have to find the maximum sum array that is starting from the right element. For example, in this example, -1 will be included in the left and the right side maximas of 4 and 2, 1 elements respectively. Recursively, we look for both left side of the element and right side of the element to find the maximum of the subarray. I know this is confusing, but I think it will be more clear after we are done with the execution of one example. Okay, let's go over the algorithm. Here I have changed the example that I've been using because it was becoming hard to show the recursion in this much space. So we have here three variables, left, right, and mid. They are helping in the recursion process, basically. And the left side and right side, these two variables are the maximum subarray that you find on the left of the middle element, and the right side is finding the maximum subarray that is possible on the right side of the middle element. And these three variables, left sum, right sum, and the combined sum, these three sum are basically making sure if the subarray has the involvement of the middle element. So left sum basically calculates the maximum sum that can be achieved for any array that is starting from first element till the left element that we have, and the right sum making sure that we have the right array which is starting from the right element and the maximum sum that can be achieved. So these are basically local maximas on the left side and the right side. And as I told you, like there are recursion variable left, right, and the mid. And a base condition is that when if left is greater than the right, then we have to return minus infinity, which is the lowest value that is possible. And then the algorithm goes like this: when we calculate the value of left plus right divided by 2, and we floor the value to calculate the value mid. And then after that, we calculate the left sum and the right sum, which is again the sum until the left element of the mid element, and the sum that is starting from the right element, that maximum sum that can be achieved from both the places. And then we calculate the combined sum, that is the sum of the mid element plus left sum and the right sum. And then after that, we recursively call on the left side and on the right side. And whatever values that we get for the left side, maximum subarray that is possible on the left side and maximum subarray that is possible on the right side. And the third value that we already calculated, which is if the mid element is involved in any way for the solution. And we return the maximum value of that, and that becomes our solution. So if you look at this example, we have four, we have five values: 5, 4, -1, and 7 and 8. And so 0 becomes the left index, and the 4 becomes the right index. Uh, and if we calculate the value of mid, that becomes 0 plus 4 divided by 2 equals to 2. So middle element is -1. And then we calculate the maximum sum that we can achieve on the left side, that is 5 plus 4, 9, because 4 element is involved in here. And the right sum is basically 7 and 8, because that is the maximum that you can get. And the combined sum becomes 9 plus 15 plus -1 equals to 23. After that, we go for that becomes the value of combined sum. Then we go for the left side. And in the left side, again, the left value gets populated as 0, and then the right value is 1, because that is mid -1. And mid value becomes 0 plus 1 divided by 2 becomes a floor value becomes 0. And we don't have any left side. That's why the recursion hits the base condition and we get the value minus infinity. And the right side, we have the value 4. That's why the recursion goes further and it tries to calculate the combined sum, which is just including the middle element, that is 4. And then we have the right and left side hitting the base condition. That's why we have the value minus infinity. And if we look at the maximum value that is possible from these three values, that is 4, and that's why left side becomes 4. Now we have in the recursion we have 9, minus infinity, and 4, out of which we have to return the maximum value, and that's why the 9 becomes populated in the left side. Then after that we go on the right side of the things, and here we look at the index has been made as 3, and the right index is 4, and the middle element is calculated as 3. So we don't have any left array anymore, so that's why the left side it becomes minus infinity, and the right sum is only one element, that's why it becomes 8, but it hasn't hit the base condition. So we'll go on a further recursion where we have the only middle element that is possible. Left side and right side has the base condition has been met. So we have the value minus infinity, and the combined sum is 8, and that's what gets populated on the right side. Now we have 8, 15, and minus infinity, and we have to return the maximum of both the values. That's why the 15 becomes the value. And then after that, we have another recursion that happens. The combined sum is 23, left side is 9, right side is 15, and we have to return the maximum value, which becomes the 23, and that's why the answer is 23 here. So as we are going in the recursion, there is a time complexity of O and log n, because we are dividing the array into two parts, and the space complexity because recursion can go until the last element in a single stack. That's why the space complexity becomes O(n). I hope it was clear. Please let me know in the comments if you have any doubt. To summarize, we looked at the first algorithm, that was brute force algorithm, and we were looking forward, and the time complexity was O(n) square and the space complexity was O(1). And the dynamic programming, we were looking backwards, and the time complexity was O(n), and O(n) this was the space complexity because of the DP array. Cadence algorithm, we have solved the problem of the DP array, and we are looking only one step back. That's why the time complexity stays the value as O(n), but the space complexity drops to O(1). And then we have the divide and conquer algorithm, which looks from the mid, and it has the time complexity of O(n) log n and the space complexity of O(n). Okay, let's go to the lead code to submit all the discussions that we have for the this problem. And here we are at the maximum subarray problem, and here I have populated all the solutions that we discussed. For example, here the first one is the brute force algorithm, and we have the start locator and the subarray finder, and we have the values of max sum and the current sum. Then we have the dynamic programming where we initialize the DP array and calculate the maximum sum, and this is how we get the index DP value, which is the maximum of DP I minus 1 plus num I and the nums I, whichever is the maximum. Then we go for the cadence algorithm where we remove the DP array and we just replace it with the current sum. And the last one is the divide and conquer, where we have the base condition here, and we are calculating the mid, then we are calculating the left sum, right sum, and the combined sum here, and then we are doing the recursion here to the divide and conquer again from the left to the mid minus 1 and the right side mid plus 1 plus comma right, and then we return the maximum value of the combined sum and the left side and the right side. And here I'm calling all the solutions one by one. And also I have created a Google Colab notebook. I have put in all the solutions that are there, and you can look at it and you let me know if you have any concerns over there. And the link I'll put in the description. So if we submit the first algorithm, that is the brute force algorithm, and we'll try to run the code, see if it is working. So now it's getting accepted, and we try to submit it. We are going to get a issue here that it is very slow. That's why it's not even accepting the solution. And that's why the time limit exceeded error message comes in. That gets resolved if we do the only dynamic programming one. So if we try to see the dynamic programming, it's getting accepted, then we submit it, and we get some success in here. But if I move to cadence algorithm here, then I'm getting submitted, but it's much faster and it is using much less memory because of the nature of the solution. And in the end, we are going to look at whether the divide and conquer is giving the right results or not. And here we are calling all these algorithms with just passing the nums. Here I'm passing with the left and right values currently, because I'm using this divide and conquer as a helper function for the recursion. And if we submit this, we are getting accepted. And then after that, if we try to submit it, and that also gets accepted, but it is much slower than the previous results as we expected that. But it is much more better way to look at the problem rather than just looking at uh, linearly. And thanks for watching, and we'll get to a new problem in the next video. Thank you.